All right, first thing we're going to do is we're going to check our answer on the Socrative app. The question here was, we have an ordinary pop can with a volume of 21.7 cubic inches. What is this volume in cubic feet? So if we get our answers locked in, we'll count down. 5, 4, 3, 2, 1. Hey, I'm feeling pretty good about this. Good. And if you didn't get it, I'm guessing that those that answered 1.81 cubic feet, what did those people forget to do?
Cube.
Right, they forgot to cube their conversion. All right. So any questions? All right, we come back to our reminders. It's all up here, extra credit practice problems, math and chemistry. Your syllabus quiz email is due today. The portion on D2L Brightspace is due tomorrow. Your element quiz. Oh, we should probably talk about that. Element quiz. On your periodic table, you have some elements here that are shaded in gray. Remember, you're supposed to be learning two things. Which two things are you supposed to be learning? Their symbol and their name. And their name with the correct spelling. The symbol should have the proper case. Now, I can give you a quick heads up here on some that are often confused with each other. Some that are often confused with each other are these two, CO and Cu. CO is cobalt, Cu is copper. Do you know where Cu comes from? What is it? Yes, that's pronounced better than I would say it, so I'll just let you say it. But it comes from, and what is that name from? Latin name, exactly. So those are often confused. Here's a couple others that are often confused with each other. They're Mn and Mg. Mg is? Magnesium. Mn is? Manganese. Now the most commonly misspelled element is this one right here. The name of this element is? Yeah, now here's a way to help you spell it correctly. If you pronounce it fluorine rather than fluorine, the correct spelling of fluorine is F-L-U-O, not O-U like flour, like your baking flour. It's F-L-U-O-R-I-N-E. And so that's probably the most commonly misspelled element. Well, then sometimes you need a little mnemonic. And I'm good at mnemonics. I have all sorts of little memory aids in here. And Zach, you might remember this one, Zachary, for these two. Hey, you! It's gold! Ah, gee, it's just silver. All right? So those two are often confused with each other as well. So again, come up with something that helps you memorize them. Probably the easiest way to learn something like this is to do what? Flashcards, exactly. And I see some flashcards back there already. All right? So put your name of the element on one side with correct spelling, flip them over, and have the symbol on the other side. And you don't even have to go through them with somebody in chemistry to get them learned. Okay, any questions on any of these? Oh, and that quiz, that element quiz, it's already up on D2L. It's due on the 10th, so we have an entire 7 days. It's open, or 6 days, I guess. It's due on the 10th, so that's a week from, well, that's next Tuesday, I guess. So it's about 6 days to get it done. And so I will remind you again on Tuesday to do it, but that is an on your own type of thing. And it's on your honor. Yes, you could sit there with your periodic table, but it's intended for this to be completed without your periodic table there. Okay? Any questions? And it's timed, so there's a practice test up there. The practice quiz or whatever is timed exactly like the graded one. So if you want to get some idea, I set up that practice quiz so you can take it as many times as you want. Okay. All right, next up, set out a demo for us. And I don't have one here on the front bench, so I'm going to get one real quick ready for you. The way I've set these up here for you is that the people that are at the ends of each row are going to be the demonstrators for your row. And so, unless you're on this side, then it's just only the person on this end. There's a couple pieces of tape. If you're in these 3 rows here, there's pieces on each of these 2 ends. Those people will be the demonstrators for your row. And what I'm doing here is I'm just taking some ordinary tape, and I'm going to put these down onto the table. And what I've done is on the very end of it, I've folded up the end to provide some handles on there. And the purpose of the handles is so that it doesn't stick to the table forever. So something you can peel up off there. Our maintenance staff, I know our maintenance staff here, they're great people. They don't like to have to come in and clean up after you. So when we're done with this, either put it in your notebooks or give you a few seconds. You can throw it in the garbage, but don't leave them stuck to the desk here so they have to clean up after you. But what this demo is going to do here is it helps us show how charges interact with each other. And whenever, now it doesn't always work the best here. We're just into September. When I do this thing in January, this works fabulous. It still works. I tried it this morning. But part of the reason why it doesn't work so well this time of the year is because there's a lot of moisture in the air. And water molecules like to pick up charged particles. Okay? So, and then in the middle of winter, there's not a whole lot of water molecules in the air. But what we're going to do is we're going to try to impart charge to these pieces of tape by ripping them up off the table. Now, when we rip them up off the table, what's going to happen is that the table could either lose electrons to the pieces of tape, or it could take electrons away from the pieces of tape. Whichever it does, it doesn't really matter, because let's say the table is something that takes electrons away. In the end, the 2 pieces of tape are going to have the same charge. And if the table is something that gives up electrons to the piece of tape, what will happen is that in the end, both of the pieces of tape are going to have the same charge. Now, it's going to be the opposite if I was wrong in one of those 2. But regardless of what it is, they're still always going to have the same charge. So let's go ahead and grab your handles. That if you're sitting there, you're going to demonstrate this to the people in your row. Grab onto those handles. Let's rip them up off the table. And then what we're going to do, if they're sticking to you, just kind of peel them back a bit here. And then what we're going to do is we're going to bring these 2 pieces of tape up next to each other. And watch what happens when you bring the 2 pieces of tape up next to each other. So what are we observing? What are the 2 pieces of tape doing to each other? They're repelling each other. Exactly. And that's because like charges will repel. Now, the next thing we're going to do is we're going to get these 2 pieces of tape to acquire opposite charges of each other. To do that, you can pass the piece of tape down to somebody else in your row now. We're going to stick the 2 pieces of tape together. You can stick it together however you wish. You can put sticky side to sticky side or sticky side to smooth side. It still works. It's going to be a lot easier to take them apart if you put sticky side to smooth side. Okay? So I'll put the 2 pieces of tape together. And I'm just going to stick them together. And then what I'm going to do is I'm going to rip these 2 pieces of tape apart. Now, if one piece of tape loses electrons, that means that the other piece of tape will gain electrons. And the piece of tape should have charges that are what? Opposites of each other. All right. So let's go ahead and do this. Rip them apart. And now if you rip them apart and they're sticking to you, just try to pull them off your fingers or wrists, then bring them together. And you should see that these pieces of tape now attract each other. They now attract. And so if you think that this is just some gimmick, pass it down to the next person. If you want to see that like charges repel, you can put them back down on the table. If somebody hasn't done this yet, put them down on the table. Leave yourself the handles on the end. Rub them down, rip them up off the table, and you should see that they will repel each other. Because, now once again, this is something you got to get down if you're not going to remember. Opposite charges will attract, like charges will repel. And this is a very quick kitchen. This isn't magic tape or anything. If you went home and tried this, maybe you want to try it with duct tape. I don't know if it works or whatever, or big pieces of packaging tape. It's something else that works. It's just a lot tougher to rip the big packaging tape up off the table. So, any questions? All right, if you want to throw it away now. Otherwise, put it in your notebook or something. Just don't leave it stuck to the table. What we just learned here is kind of essential to some of the things that we are going to look at here today. And so the next thing we are going to look at is this device here. This is a device called a cathode ray tube. These used to be very common. Not so common anymore. Where did we find cathode ray tubes all the time? Old TVs, exactly. We had the big old boxy TV. Those are ones that contained a cathode ray tube in them. And one of the reasons they were so heavy is because inside of them they contained a magnet, and that magnet would deflect and direct the beam of electrons towards your screen. And so the image on the screen was produced by electrons hitting the phosphors on the screen, and yeah, again, the image is what wound up resulting. Now, this here is a very simple cathode ray tube. When you look at its construction, you're going to see that it appears that the bottom of this is melted, and that's exactly what it is. What was done is that this was hooked up to a vacuum pump, and then all of the air was withdrawn from it, and then it was melted shut. And so before we did that, we stuck a small metal strip in there and coated this metal strip with a substance called zinc sulfide. Now, the original cathode ray tubes, if I were to dim the lights here entirely, we'll even pop this down a bit here. The original cathode ray tubes would have been designed without this metal strip in there. And if you look at this and see this kind of you might be able to see a purplish glow in each of the ends. That's what the original cathode ray tube would have looked like. We put this metal screen in here with the zinc sulfide coating, so you are able to see here in the class what's observed. And so if I take this magnet now and bring this magnet towards this beam, you can see that what happens is that this beam gets deflected downward. Okay, then what I'm going to do is I'm going to flip this, 50,000 volts here, by the way. Okay, if I now take this, let's check this out here. First off, I'm doing this side, you see how it's being deflected downwards. What I'm going to do now is I'm going to flip this magnet over, and I'm going to put the other side up here. And notice now when I bring this side towards the beam, what's happening instead? It's being deflected, hopefully, upward, right? There we go. So this side causes it to be deflected upward. This side here causes it to be deflected downward. And in the original cathode ray tube, instead of using these magnetic fields, instead what was done is that charged plates were placed up here. So again, in the place of a magnetic field, charged plates were placed in. And when the charged plates were placed in here, I'm going to try to assign the charge here now. This side here is a positive charge, and this side here is a negative charge. So we see it's being bent towards the positively charged plate. So when this is done, what we're showing is that these cathode rays bent towards the positively charged plate. And if they're bent towards a positively charged plate, let's put our answer here into our Socrative app. What does that mean? So again, in the cathode ray tube experiment, and this was conducted by a scientist by the name of J.J. Thomson, that cathode ray was bent towards the positively charged plate, meaning that the cathode ray is, and we'll get our answers locked in. We'll count down 5, 4, 3, 2, 1. Great. Means it was negatively charged. And one of the things that was done in this experiment, and one of the results is it helped Thomson to calculate what is called the mass to charge ratio of the electron. And we label it as m over E. So this experiment for Thomson enabled him to find what's called the mass to charge ratio. The other thing it did is that it showed that all atoms contain these same electrons. And this was the first step. Before Thomson's experiment, there was not a lot of evidence that showed that atoms were divisible. Up to this point, it was believed that, oh, yeah, an atom, in fact, if you were to look at the word atom, the atom comes from the Greek word atomos, which means indivisible, or can't be divided. And so this was the first experiment that showed that the atom was indeed divisible, could be broken up into smaller pieces. And so what Thomson did to further prove that, if you were to look in here, this is the cathode down here. This particular one, I don't know if this is aluminum or iron. I believe it's aluminum. So what Thomson did then is tried placing different substances in here as the electrode, and regardless of the element that was used as the electrode or the cathode down here, all of the cathode rays behaved in an identical manner. And so not only did it help determine what is called the mass to charge ratio of the electron, it also showed that all atoms contain these electrons. Okay, so any questions on that particular demo? Okay, next one. There was a scientist by the name of Robert Millikan, and he conducted an experiment called the oil drop experiment. Now, I don't expect you to remember names and dates. If you want to have some idea, the Thomson experiment here was 1897. The Millikan oil drop experiment that we're going to look at here next is about 1909. The Rutherford alpha scattering experiment is about 1911. Again, though, I don't test on names and dates. This isn't history, but this is just giving credit for some of these big experiments in terms of our understanding of the atom. And so this is a little video on the Millikan experiment and what it showed.
1.6 times 10 to
Oops.
the minus 19.
We got to start at the beginning. How about that?
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
Okay. So again, that's the Millikan experiment that came up with the charge in the electron, and that was a step here from Thomson's experiment, which he showed the mass to charge ratio. And as far as how these oil drops picked up their charge, it's very similar to the way that we got these pieces of tape to pick up charge. Just like you pick up charge in the winter. If you are dragging your feet across a carpeted surface or whatever, you know that if you approach a piece of metal, you might wind up getting a shock. It's simply because there's charge transferred whenever there's some sort of friction. So in Millikan's experiment, those tiny oil drops would pick up a very small amount of charge simply by the fact that when they get atomized or produced in this mist, they would pick up those small charges. And then there was an experiment by the name of Ernest Rutherford, This is an alpha scattering experiment. And as far as how this is set up, this is the basic setup of it. There was a box made of lead, and into this box made of lead there was placed what's called an alpha source. And we'll say it's a radioactive alpha source. And what's important to know about the fact that it's an alpha source is that alpha particles are relatively heavy, positively charged particles. So took an alpha emitter, an alpha source, placed it inside of this lead block, and then directed it at the piece of gold foil, and upon doing so observed the behavior of what happened. And so I have another video here that talks about Rutherford's experiment. I'll drag this back.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
All right, now let's see, based on some of what we've already learned here today in our tape demo, if you can answer a few basic questions. So think, before you answer, don't just throw in an answer. What do you think it means if most of the alpha particles, which again are relatively heavy, positively charged particles, what would it mean if most of them pass straight through the gold foil? Does it mean that the atom is filled or solid? Does it mean it's mostly empty space? Does it mean it's mostly positively charged or mostly negatively charged? So we'll get our answers locked in here, please. We'll count down. 5, 4, 3, 2, 1. Correct answer is it is mostly empty space. If they're not running into anything, that is if they're going straight through, that means that they're not running into anything. It has to mean that they're mostly empty space. Sure, the electrons are there, but the electrons are so tiny that they're not running into any of those electrons, so they're passing straight on through. Now that's kind of hard to believe, because when you look at an atom, if it's most empty space, it's really like 99.99999% empty space. I mean, there's just a super tiny fraction that is in empty space in an atom. And so when you look down on a table, for example, like this, and you might say, well, wow, how in the world could those atoms be mostly empty space? Because certainly when you look down here, it doesn't look like it is very empty at all. You don't see through it. And so how could it be empty? And so one of the analogies I'd have for you is this. Now when I was a kid, one of the things that I did a lot, I lived out in the country, and kids actually used to play outside, okay? And we used to beat the crap out of our bikes. And so when we beat the crap out of our bikes or whatever, we'd have to fix them. And so we would have to flip them upside down, replace tires or whatever. But one of the things that we like to do is we'd turn them upside down and we'd start cranking the pedals. We'd try to crank them really fast and get the tire to spin. And then we'd stand off to the side and we'd throw rocks and we'd try to throw them through the spokes. Well, what do you think happens when we start trying to throw the tires through the spokes? Well, most of those wind up going straight through. But every now and again, what would happen is a rock would hit one of those spokes and get kicked off. Well, why would most of those rocks go straight through?
space.
It's mostly empty space, exactly. Okay, now, how does that compare to this? Well, let's say now we look at this table here, and we're not talking about this just being one atom thick. Literally, they are it's like 10 to the something huge number of atoms thick here. We're talking about trillions and trillions and trillions of atoms thick that we're looking through. And so now the analogy I would have, instead of looking at a single bicycle wheel spinning around, let's say instead of taking a single bicycle, we would line up like about 1,000 bicycles. And everybody's going to start sitting there spinning their tires around. And you start looking through down there, what do you think you're going to see if you have 1,000 of those that you're trying to look through? Well, all of a sudden that space begins to fill up, so to speak. Okay? And that's why if we try to shoot something here through this table is extremely thick. It's not going to go through. In Rutherford's experiment, that was an extremely thin piece of foil that he was trying to pass through those. Now the second piece of the Rutherford experiment is that while most of them passed through, there were a few alpha particles that were deflected at small angles, and some of them even bounced back. What does that mean? What does that mean? So we'll get our answers locked in here, please. And we'll count down on this. 5, 4, 3, 2, 1. Means that we have an extremely dense, positively charged nucleus. First of all, it has to be extremely dense because, again, what happened to most of the alpha particles? They pass straight through, right? So the nucleus couldn't be very large. Means that that nucleus has to be very tiny and extremely dense. And why is it positively charged rather than negatively charged?
Gold positive.
What's both positive?
The gold's positively charged.
Well, not the gold itself, but the nucleus is, right? So the nucleus is positively charged. Why would this show, though, that it's positively charged?
The alpha particles are also positively charged.
The alpha particles are also positively charged, exactly. So the fact that they repelled each other is the fact that that nucleus must be positively charged. Now, an analogy I would make when we talk about it being extremely dense, this is extremely dense beyond anything you and I can comprehend. Okay? And as an analogy, let's say that we were to compare the nucleus to an atom. If you've ever been into a large stadium like Target Field or US Bank Stadium or the old Metrodome, if you were to have a housefly inside that stadium, comparing the size of the housefly to the size of the stadium is like comparing the size of the nucleus to the size of the atom itself. So there's a very huge difference in terms of the size of the nucleus to the size of the atom. And when we talk about its density being extremely dense, again, it's beyond our comprehension. If you want to get an idea of how dense that is, let's say that we went to a place like US Bank Stadium and we filled that entire stadium up with lead. I think we'd all agree that that is going to be a very heavy, massive amount of lead. If all of a sudden then we took and removed all of the empty space from those atoms, all that would happen is that all of that lead in that stadium would wind up collapsing down to the size of that housefly, but that housefly would have the mass of the entire stadium filled with lead. Okay, so that's how we're talking about the extreme density of the nucleus. It's beyond what anybody in here is capable of comprehending. Okay, so any questions on those? Okay, finally, which experiment led to the determination of the charge on the electron? Was it the cathode ray tube experiment, the oil drop experiment or the alpha scattering gold foil experiment? And we'll get our answers locked in, please. We'll count down. 5, 4, 3, 2, 1. And that there was the oil drop experiment. And I'm not going to cover that in great detail here. I believe that one of your questions on the assignment for this chapter will have a Millikan oil drop experiment activity for you to go through. All right, we're going to move on here. Any questions on these? Okay, next up we're going to look at some subatomic particles. And of course the 3 primary subatomic particles that are of interest to chemists are what? What are the 3? What's one of them? Electrons. What's another? Proton and neutron. Understand though that these are only 3 types of subatomic particles. There have been over 100 different types of subatomic particles that have been identified. That is particles that are smaller than atoms. But to the chemist, these are the ones that matter most. Today we find out, for example, that protons and neutrons themselves are comprised of still smaller particles. Anybody know the still smaller particles that protons and neutrons are made out of? Quarks, exactly. They're called quarks. And so each proton, each neutron is comprised of 3 quarks. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. So, as far as what you would be expected to know of these, we should have an abbreviation that we're familiar with, which should all make sense. So it's E, P, and N I'll be using. You should know their charges. The charge of an electron is negative. Proton it is positive, and neutron it is neutral. And very often we indicate the degree of charge by, I heard somebody say the 1. So we'd say 1 negative and 1 positive. And by the way, I am not writing these wrong. I know it's very disturbing to some people to see the sign after the number, but this is the correct way to write them. When we want to show the charge on a particle, the sign comes afterwards. When we want to show a positive or negative number, we show the sign in the front. So if you're showing these with the sign in front, you are not indicating a charge. So if you want to indicate charge, you show the sign after the number, not before the number. And so sometimes we write the symbols as E negative, P positive, and N with a superscript of 0. And then you should know their masses, approximate masses, in units of AMUs. And we define an AMU as an atomic mass unit. Again, we abbreviate that as an AMU. And we define this as being 1/12 of the mass of an atom of carbon-12. We haven't really talked about what it means yet about when we write a number after the name. We'll talk about that a bit here today. But we define the atomic mass as being 1/12 of the mass of an atom of carbon-12. And part of the reason why we do that is that if we look at our conversion sheet here now, what we see when we look at the conversion sheet is that down here we have masses, and those masses expressed in kilograms are extremely tiny. They're on the order of 10 to the negative 27th all the way down to 10 to the negative 31st grams. So because they are so tiny, we express them in much more convenient numbers, which are going to be closer to whole number values. And so the approximate mass, I'm jumping down here to the proton, the approximate mass of a proton in AMUs is about 1. For a neutron, it is about 1. And for an electron, we say it's about 0. And I'm putting in the about symbol because it does have some mass. And we say it's about because it's not exactly these values. If it's going to be exactly 1, it's going to be 1/12 of the mass of an atom of carbon-12. But we give these approximate values because they're going to give us a chance to very quickly wind up calculating masses for some of the things we're looking at here next. Okay, next up, let's look at the atomic number. We're going to look at two things there, the atomic number and the mass number. Now the atomic number is something that we abbreviate with the letter Z. We abbreviate the mass number with the letter A. And don't ask me why, it doesn't make any sense whatsoever. To me it makes sense to call the atomic number A and the mass number maybe an M or something, but the atomic number goes by the letter Z, the mass number goes by the letter A. And if we come back to the periodic table, where do we find, let's say we use oxygen as an example. What is the atomic number of oxygen? 8, exactly. So this here, this top number in the box represents the atomic number, or the Z value. Now if you look at this periodic table, you will not find the mass number on here. Rather, what you're going to find is you're going to find this value down here, which is called the atomic mass. So the top number here is the atomic number, and the bottom number is the atomic mass. And what this atomic mass represents, just so we're on the same page, is it represents the average mass. So the atomic mass represents the average mass of all the naturally occurring isotopes of a given element. Which brings up yet another word we have to define, and that word appears to be isotopes. And we say that isotopes are atoms of the same element that have a different number of which particle? Neutrons. Exactly, different number of neutrons. So we've brought up a whole bunch of different words here. We still haven't really defined what the atomic number is. We showed what the atomic number is, but what is the atomic number equal to? Number of protons. So this here is equal to, it equals the number of protons, and I'll just give it its abbreviation. So it's equal to the number of protons in the nucleus of one atom of that element. And the mass number, this here equals the sum of the protons and neutrons in the nucleus of one atom of that particular isotope. So the atomic number is the number of protons, the mass number is the sum of the protons and neutrons. Now, how all that works, we'll kind of piece it all together, would be something like this. And I forgot to bring this up here before I came into class today. So I'm going to have to do a quick search here. Let's see if I can bring this up. Ice. It's not going to let me type. Alright, so let me put this up here. Web. Let's try looking at this web address. There we go. This is the one that I like to use. It's the Web Elements Isotopes. And now, how do I get rid of this thing? It's trying to type or something. Great. Well, it registered my I after how long, right? There we go. Alright, so I'm not going to use that again, that's for sure. Okay, so if we come back here and look at this, skip all ads. Sure, let's do that. If we come to something like oxygen, what we're going to see is I'm going to click on oxygen here, and we're going to find out that oxygen has 3 naturally occurring isotopes. And the way we can write them, this is one of them, is we write them with superscripts to the left of the symbol. And so we see that we have what's called oxygen 16, oxygen 17, and oxygen 18. So again, I'm going to write this down. They are oxygen 16, oxygen 17, and oxygen 18. Once again, these are the 3 naturally occurring isotopes of oxygen. There's more than 3 isotopes of oxygen, but these are the 3 naturally occurring isotopes of oxygen. And one of the ways that we could write this would be as O-16, O-17, O-18, or as we saw on there already, we saw them as superscripts to the left of the atomic symbol. So we could write it like this. And then there's the way that your author will be writing them, and I will usually be writing them this way, is write them with both superscripts and subscripts to the left of the chemical symbol. So this is how I will generally write them. And so when it's written in this form right here, this form right here is called the nuclide symbol. Sometimes we call it the isotope symbol. Now, if you were a particle physicist, you would make a distinction between nuclides and isotopes. Technically, a nuclide just refers to the nucleus. We as chemists aren't so concerned about nuclides. We're more concerned about the entire the nucleus. Chemists are more concerned actually about the electrons, so we refer to them as isotopes. Again, a particle physicist probably refer to them more specifically as nuclides because they're more interested in looking at what happens to the nucleus. But when we look at this then, the nuclide symbol is written in this format. So here's a generic nuclide symbol like this. And up above, we put the A value. Down below here, as a subscript to the left, we put the Z value. Remember now that the Z value, which appears as a subscript, represents the which value?
Atomic number.
Atomic number. The superscript up here, the A value, to represent the mass number. And next here then would represent the chemical symbol itself. So by looking at the nuclide symbol, the information we can get off of here would be this. We can determine the number of protons and the number of electrons and the number of neutrons in one atom simply by looking at the nuclide symbol. So again, if we know that Z is the atomic number and A is the mass number, how many protons would there be here in oxygen 16? How many protons? All right, how many electrons would there be? Because the number of protons in a neutral atom is always equal, I think I said this wrong. The number of electrons in a neutral atom is always equal to the number of protons. However, the Z value here always represents the number of protons. The electrons, since they are on the outside of the atom, they are the ones that are gained or lost, and so we can form ions. When ions form, the number of electrons change, the number of protons does not. How many neutrons would this one have? 8 as well. Let's go to the next row. Oxygen 17, how many protons? 8. How many electrons? 8. How many neutrons? How can we tell? There's 9. Next one. How many protons? 8. How many electrons? How many neutrons? 10. Now, I didn't tell you how to do those. Let's see if you can figure it out by going to our Socrative app. How many neutrons are there in titanium 50? Please talk this out. If you're unsure, don't just put in a random answer. Talk to neighbor.
So there's 22 protons. So we just do 50 minus 22.
I'm going to give you 30 more seconds. And if you haven't figured it out, you talk to someone that seems to have it figured out. We're going to count down on this one. 5, 4, 3, 2, 1. 28. Great. You got it figured out. Because how do we do it?
50 minus 22.
50 minus 22. The number on top is called the mass number. The one on the bottom is the atomic number. Remember that the mass number is the sum of the protons and neutrons. The atomic number is simply the protons. So you subtract to get them. Read carefully. Molybdenum 94 has how many protons? And we'll get our answers locked in here, please. We'll count down. 5, 4, 3, 2, 1. Correct answer here, of course, is 42. Because the number at the bottom on there is called the atomic number. An atomic number is always equal to the number of protons. Good. Okay, now for the next two here, let's do this. Have an example where we have 19 protons, 19 protons, 19 electrons, and 21 neutrons. Write its isotope symbol. And do the same thing for one that has 83 protons, 83 electrons, and 127 neutrons. Write the isotope symbol for each of these two. And they will show up in order on the Socrative app. Okay, let's see how we're doing. All right, let's get our answers locked in here, please. And by the way, they're a little bit offset because in this particular app, when I put them in, I can't stack the superscripts and subscripts. So we'll count down on this. 5, 4, 3, 2, 1. Great. Let's look at the next one. And we're going to get our answers locked in here, please. We'll count down. 5, 4, 3, 2, 1. Great. It's bismuth 210. We don't need to discuss that. Looks like we've done well. So let's go on then and look at how we determine how many isotopes there are for an element. And to do that, looks like I need to go on to this next one here. Here we go. We use a device called a mass spectrometer. A mass spectrometer. And the way that a mass spectrometer is set up is something like this. If we want to determine the number of isotopes, what we do is a sample gets injected into the mass spectrometer, which is what the device again is called. And it has to be injected into the mass spectrometer as a gas. So even if we're talking about an element like tungsten, which has a melting point, or excuse me, a boiling point of like over 5,000 kelvins, we need to vaporize it, get into the gaseous phase first, and then once it's in the gaseous phase, what will happen is that it is going to encounter a beam of electrons. And those beam of electrons will wind up ionizing the sample and basically winds up stripping electrons off of that particular element. When it does so then, what will happen is that we have some magnets that are down here. These magnets wind up attracting those particles, very much like when we saw the magnet being used on our cathode ray tube here. There was an attraction towards the magnet. And these are going to be extremely powerful magnets. So what happens is that these particles will accelerate down this path. Well, when they encounter these magnets then, just like we saw with this one here, this magnet deflects or bends the beam. What will happen is that if this element was chlorine, now this one isn't showing chlorine, this must be showing something else. Because when it comes down here, notice there's how many different paths that wind up forming. Winds up forming 3 distinct paths. And it winds up forming 3 distinct paths. This particular element we would say has 3 different isotopes. Okay? Now, why it forms different paths is because each of them has that different mass. Be very much like comparing me to, say, one of the smaller people in this classroom. If we're out on a football field and we start running down at the same speed and somebody else tries to bump us off our path, whose path is going to change much more easily? Is it going to be my path or the much smaller person?
Much smaller.
The much smaller person going to wind up getting bumped off that path a lot easier. And the same is true with these charged particles. The lighter ones are going to wind up being deflected more, and the heavier ones will be deflected less. So again, we wind up with the different paths based on mass, simply like, again, if you're on a football field or something, somebody runs into you, somebody larger like me you're going to have a more, it's not that I'm trying to brag or anything, but just simply because I am heavier, it's going to be harder to move me than it is to move a smaller person. So the same is true of these particles in here. It's going to be much more difficult to move a heavier particle than is a lighter one. So we wind up with a number of paths. If we wind up with 6 different paths down here, that would mean that the element would have a total of 6 different isotopes. In the case of chlorine, if chlorine was done, chlorine winds up having 2 different paths because chlorine has 2 different isotopes. Now, the question might come up then, how many naturally occurring, is there a way to figure out by looking at the periodic table? We're looking at the periodic table here, and if I said to you, how many naturally occurring isotopes does oxygen have? Well, we went through it already. It has 3, but the only way that you would know is that if we looked it up. There's no way that you can look at the periodic table and tell that oxygen has 3 naturally occurring isotopes. Because the element right next to it, fluorine, has only 1. But if you went down to tin right here, turns out that tin has 10 naturally occurring isotopes. So simply looking at the periodic table, there's no way to tell how many naturally occurring isotopes there are. With this exception, and if you've had me before, you know this one, you can tell the elements that have 0 naturally occurring isotopes. And how can you tell by looking at this periodic table which ones have 0? Any ideas? Can I put you on the spot, Zachary?
I don't remember.
You don't remember? Yeah, go ahead.
Like the ones that are not filled in.
Yeah.
Natural elements.
Exactly. It's the ones that are here in outline letters. These here have 0 naturally occurring isotopes. Now, when you look on your periodic table, if you want to tell, look at yours, and how do your elements appear that have 0 naturally occurring isotopes? Right. Yours are the ones on the periodic table that are italicized. And again, the italicized ones have 0 naturally occurring isotopes. So those are the ones that you should know. If we went out and dug up some dirt or looked at the gases in the atmosphere, we would not find any of these elements out there that are naturally occurring. The ones that are in italics. For all the rest of them, if you want to know the number of naturally occurring isotopes, you need some resource like I just Googled when we came in here, and that was, and I will link this to our D2L course, but if you want to do it yourself, you just go to Web Elements Isotopes. If you look up Web Elements Isotopes, then you're going to get this periodic table right here, and this one shows the isotopes of those elements. So if I went to fluorine and clicked on this, and look down, we would see that fluorine has just that 1 naturally occurring isotope. And if I come back here and look at tin, like I mentioned, we'd see that tin has a total of 10 naturally occurring isotopes. Now, all of these elements have more isotopes than are naturally occurring. They just don't occur in nature. So for example, something like oxygen, there's probably 10 different isotopes that are known for oxygen. They go probably all the way from oxygen 12 up to oxygen, well, there's probably more than that. It's probably like oxygen 12 or 13, all the way up to about oxygen 25 or 26. Okay, but of those, only 3 of them are naturally occurring. And so when you use this isotope table, or if you look up an isotope table, typically the ones that they're going to give you are these here, the ones that are considered to be naturally occurring. So, as an example, if we come back here to one of the things that we defined here today, we defined the atomic mass as being the average mass of all of the naturally occurring isotopes of that element. So it is the average mass of all the naturally occurring isotopes of that element. And so let's say we want to look at an example of something like chlorine. Chlorine here has 2 naturally occurring isotopes. This, by the way, what this plot represents, this is called a mass, I'm trying to think of what it's called, a spectrogram. of chlorine. And so the heights of these here, in terms of their intensity, represent their relative abundances to each other. And so the most abundant one, when this is put out, the most abundant one is said to have a 100% intensity, so to speak. And then the other ones, the other peaks, are measured relative to that. And I think we saw something like that when we pulled up some of these graphs. Here's what the pattern looks like for tin. And so on this graph right here, it looks like the most abundant of those isotopes is tin 120. Okay? So then what is done is that the heights of all the rest of them are measured relative to the tallest one, and then the net result is these numbers here that are blue down below wind up being the percent of their relative abundance. So if we look at something like chlorine, coming back to it, we should expect to find two peaks here. And there we go. We have their heights relative to each other about 75.76 to 24.24. So now if we wanted to use this information to calculate the atomic mass, let's look at such an example. Let's calculate, and I can probably put it on this one right here. Let's calculate the atomic mass for chlorine. Let's calculate the atomic mass for chlorine. Now to do this, we need our two isotopes, which again are chlorine 35 and chlorine 37. We need the masses of each of these isotopes, which are given in units of AMUs. We also will need their relative abundances. So to do this, we'll come back to our data here and we'll fill this in. So look at chlorine. Now I'm not going to write out all these digits. Let's go out to about the 10,000th place. So chlorine, let's write down 34.9689. So 34.9689. And for chlorine 37, looks like it's 36.9659. So 36.9659. And for the relative abundances, this is given here in a percent abundance. For chlorine 35, it's 75.78%. For chlorine 37, it's 24.22. So again, 75.78% and 24.22%. Now before we calculate it, let me just go back and show you this piece right here. Remember, what do we call this number up above? The superscript is called the mass number. We define the mass number as being the sum of the protons and neutrons. Remember that each proton has a mass of about 1 AMU. Each neutron has a mass of about 1 AMU. So if we have a total of 37 particles, each having a mass of about 1 AMU, we'd expect the mass of that isotope to be about that mass. So this mass number is the approximate mass of that isotope. That's a fact you should know. Is the mass number is the approximate mass of that isotope, but it's only approximate. It's only to the nearest whole number. And that's because again, each proton and each neutron has a mass of about 1 AMU. So now to calculate this, if we're going to calculate the average mass of all the naturally occurring isotopes, the temptation might be to sum these two together and divide by 2. That would only work if this percentage is 50-50. We have to calculate what's called a weighted average. So what we're going to do is we're going to change each of these percentages into their decimal equivalent. To change them into the decimal equivalent, we have to move the decimal place over 2 spots. We get this here. And then we're going to multiply each of their masses by their relative abundance. And so we'll take 34.9689, multiply that by 0.7578. We wind up with 26.4994. I'm not going to worry about rounding just yet. Then if we do the second one, we'll take 36.9659 times 0.2422, and that's going to give us 8.9531. Now if we look at significant figures, because the operation here is multiplication, that means that the uncertain digit in this case is the fourth significant figure. So I'm underlining the uncertain digit. If we sum these on down, we take the 26.4994, add it to 8.9531, and we get 35.4525. But because this here is the uncertain digit, when we add and subtract, we go by decimal places. That tells us that this digit is the uncertain digit. Means we're going to round off to this value. That tells us that the atomic mass for chlorine would be 35.45 AMUs. So this here is the atomic mass for chlorine. And if we come back to our periodic table, we look at chlorine, we're going to see that that mass here is given as 35.45. And so that's where all of these values come from in the periodic table, is they come from a weighted average of all those naturally occurring isotopes of that element. Now, other things you can do with this, for example, let's say that I would look at something like boron right here. And I told you that boron had two naturally occurring isotopes. They are boron 10 and boron 11. If you know that boron has two naturally occurring isotopes, which of those two isotopes is more abundant? Boron 11, because?
Closer to 11.
Closer to 11. And if I told you that bromine over here has two naturally occurring isotopes, those two naturally occurring isotopes are bromine 79 and bromine 81. Bromine 79 and bromine 81, what could we guess about the relative abundances of those two isotopes?
Pretty equal.
Pretty equal. If they're going to be closer to one, it's probably closer to 79. And if you were to come back here and look at something like bromine on our table of isotopes, you would see indeed that bromine does have two naturally occurring isotopes. They are about equal, but the one that's more abundant is going to be, in fact, the bromine 79. So while you can't tell the number of isotopes on the periodic table, if you do know the number of isotopes, you can very often figure out which one is the most abundant. Okay. Any questions on that? All right. Last thing we're going to look at here today, and then I'll have a few more Socrative app questions for you, is the concept of ions. And we say here that ions are atoms or groups of covalently bonded atoms that have gained or lost one or more electrons. So now, the way that we write an ion is something like this. So let's say that we look at calcium with a 2 positive charge. We wrote down calcium with a 2 positive charge. You should be able to figure out which particle in this ion is more abundant. Are there more protons or more electrons in this ion? Because the charge is positive. And how do we figure out the number of protons? How many protons would one of these atoms have? And how would we know? Periodic table. So if we look at the periodic table, how many protons would calcium have? Here's calcium. How many protons? 20. So we come back here and we say it has 20 protons. How many electrons is it going to have? 18. And how do we get the 18?
Subtract the 2 from the number of protons.
Right, subtract the 2 from the number of protons. Because it's 2 positive, we know that there's more protons than electrons. The number of particles that never changes here is going to be the number of protons. Okay, these are the last 2. Try these out. And I believe this is how we will wrap up today. We have the nitride ion and we have the sodium ion. Remember, I'm not writing these incorrectly. We write the charge after the sign. So in each one of these, determine the number of protons and the number of electrons. The nitride ion and the sodium ion. Always feel free to discuss your answers. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. We need to get up to 20 respondents at least here. We got 13 of you. Let's get a couple more in there. Answers in. And let's count down on this. 5, 4, 3, 2, 1. There are 10 electrons. So since we have a fair number that got it wrong, how many protons are there in a nitrogen atom? 7. So if the charge is 3 negative, that means there are more electrons. How many more? 3 more. So 7 plus 3 is going to give you 10. How many electrons are there in a sodium ion? And we'll get our answers locked in here, please. Count down. 5, 4, 3, 2, 1. There are 10 of them. All right. And that's because sodium by itself, come back here, sodium has how many protons? 11. That comes from the atomic number, so it has 11 protons. Charge is positive. That means that there's more protons than electrons. There has to be 10 electrons. That's it here for today, folks.